Welcome back to G Fun Facts Online. Today, we are going to take a deep dive into one of the most fascinating, frustrating, and ultimately illuminating ghost stories in the history of science. This is not a story about hauntings or supernatural spirits, but about the ghost in the machine of reality itself, the neutrino. Specifically, we are going to talk about the rise and fall of the fourth neutrino, the sterile neutrino, and how a massive machine called MicroBooNE stared into the void and found nothing but silence. It is a story of scientific detective work, of anomalies that refuse to die, and of the incredible technology we build to hunt for things that are barely there. To understand why this recent result from late 2021 was such a bombshell, we have to step back and look at the cathedral of particle physics, known as the Standard Model. The Standard Model is arguably the most successful scientific theory humans have ever devised. It describes the fundamental building blocks of the universe with exquisite precision. But for the last 30 years, there has been a whisper coming from the basement, a persistent suggestion that the model is incomplete. That whisper comes from neutrinos. Neutrinos are the most abundant matter particles in the universe. They outnumber atoms by 1 billion to 1. Right now, as you listen to this, trillions of them are passing through your body, through the Earth, and out the other side, without touching a thing. They are electrically neutral, they have almost no mass, and they barely interact with the rest of the universe. They are ghosts. For a long time, we thought we understood them. We knew there were 3 types, or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. But the trouble began in the 1990s with an experiment called LSND, the Liquid Scintillator Neutrino Detector, at Los Alamos National Laboratory. LSND was looking at how neutrinos travel, and they saw something that should NT be there. They saw an excess of electron antineutrinos appearing over a short distance. According to the Standard Model, this should NT happen. Neutrinos can change flavor, a process called oscillation. But the rate at which they were doing it in the LSND experiment implied that they were interacting with something else, something we hadn't discovered yet. To make the math work, to explain this weird excess, physicists proposed a 4th neutrino. But this couldn't be just any neutrino. You see, we already knew from experiments at CERN involving the Z boson that there are only 3 active neutrinos that feel the weak nuclear force. If there were a 4th one that felt the weak force, the Z boson would decay faster than it does. So if this 4th neutrino existed, it had to be invisible to the weak force. It wouldn't feel electromagnetism, it wouldn't feel the strong force, and it wouldn't feel the weak force. It would only interact with the universe through gravity and by mixing with the other neutrinos. It would be a ghost, even to other ghosts. They called it the sterile neutrino. This was a seductive idea. A sterile neutrino wouldn't just explain the weird data from Los Alamos. It could potentially solve some of the biggest mysteries in cosmology. If it had the right mass, it could be dark matter, that invisible scaffolding that holds galaxies together. It could explain why there is more matter than antimatter in the universe. It was a perfect puzzle piece. But science demands verification. You cannot just rewrite the laws of physics based on one experiment. So physicists built a new experiment called MicroBooNE at Fermilab outside Chicago, specifically to check the LSND result. MicroBooNE ran for over a decade. And in 2018, they dropped a bombshell. They didn't just see the same thing LSND saw, they saw it with even higher significance. They observed a massive spike in electron-neutrino-like events at low energies. This was called the low-energy excess. The statistical significance was 4.8 sigma, which in physics speak means there is less than a 1 in a million chance that it was a fluke. The combined data from LSND and MicroBooNE screamed that the Standard Model was broken. The sterile neutrino hypothesis looked like the winner. But there was a catch, and it was a big one. It came down to how MicroBooNE actually saw the world. MicroBooNE was a Cherenkov detector. It was a giant tank filled with mineral oil. When a neutrino hit an atom in the oil, it produced a charged particle that moved faster than light moves through oil. This created a shock wave of blue light, called Cherenkov radiation. Photomultiplier tubes lining the tank would catch this light. The problem was that MicroBooNE had fuzzy vision. In a Cherenkov detector, an electron produced by an electron neutrino creates a fuzzy ring of light. But a photon, a particle of light, creates a signal that looks almost exactly the same. If a background process produced a single photon in the tank, MicroBooNE couldn't easily tell it apart from an electron. So the big question hung in the air. Was the low-energy excess really evidence of ghost neutrinos transforming into electron neutrinos? Or was it just a misunderstood background of photons mimicking the signal? MicroBooNE simply couldn't tell the difference. It was like trying to identify a face in a low-resolution security video. To solve this, we needed a better camera. Enter MicroBooNE. This is where the engineering gets truly heroic. MicroBooNE was designed to use a technology called a liquid argon time projection chamber, or LARTPC. Instead of mineral oil, it uses 170 tons of liquid argon, chilled to -186 degrees Celsius. When a neutrino smashes into an argon atom, it creates a spray of charged particles. These particles strip electrons off the argon atoms as they travel, leaving a trail of ionization, like the contrail of a jet plane. A massive electric field pulls these ionization electrons to a wall of thousands of fine wires. By measuring when and where the electrons hit the wires, computers can reconstruct a 3D image of the event with millimeter precision. If MicroBooNE was a fuzzy security camera, MicroBooNE is 4K Ultra HD. Crucially, MicroBooNE can tell the difference between an electron and a photon. Here is the key detail. An electron tracks through the argon and starts ionizing immediately, attached to the interaction point. But a photon is neutral. It travels a short distance invisibly, a few centimeters, before it converts into an electron-positron pair. This creates a gap. MicroBooNE is sharp enough to see that tiny gap. It can look at the event and say that is not an electron, that is a photon. The experiment began collecting data in 2015. For 6 years, the team, comprising nearly 200 scientists from around the world, analyzed the neutrino beam. They blinded their analysis, meaning they locked away the actual data in a hidden box, and worked only on simulations and sidebands to calibrate their algorithms. They used cutting-edge artificial intelligence and deep learning to identify the particle tracks. They wanted to be absolutely sure that when they opened the box, they wouldn't bias the result. Finally, in late 2021, they were ready. The world of physics held its breath. If they saw the excess of electrons, the sterile neutrino was real, and we would have discovered a new fundamental particle, the first beyond the standard model. If they didn't, the most popular theory of the last 20 years would be dead. On October 27, 2021, they announced the result. They looked into the heart of the anomaly, searching for that specific excess of electron neutrinos that MicroBooNE claimed to see, and they found nothing. The data was perfectly consistent with the standard model prediction of 3 neutrinos. There was no pileup of electron events. The result ruled out the simple sterile neutrino hypothesis with exceedingly high confidence. They also checked the photon background hypothesis, investigating if a specific type of radioactive decay was fooling the detectors. They found that the background was well understood and could not account for the anomaly either. So, what does this mean? It means the simple explanation is wrong. The idea that a single, stable, sterile neutrino is responsible for the MicroBooNE anomaly is effectively dead. MicroBooNE proved that the signal MicroBooNE saw was not simply electron neutrinos appearing out of nowhere. But here is the twist, and it is a delightful one. MicroBooNE did not prove that the anomaly didn't happen. The MicroBooNE detector really did see flashes of light. The LSND detector really did see something strange. The universe is still shouting at us that something is wrong, but MicroBooNE has told us that our translation of that shout was incorrect. We thought it was saying sterile neutrino, but it might be saying something much more exotic. This brings us to the new frontier. Now that the simple ghost is gone, physicists are looking for even stranger things in the data. The void left by the sterile neutrino is being filled with theories from the dark sector. One leading candidate is the idea of dark tridents. Imagine that the neutrino beam contains not just neutrinos, but also dark matter particles or dark photons. A dark trident event occurs when a dark particle interacts with the argon and creates an electron-positron pair plus a neutrino. To MicroBooNE's fuzzy eyes, that overlapping electron and positron would look like a single electron track. But MicroBooNE might be able to see the two distinct tracks if they are just wide enough apart. The hunt for these dark tridents is now on. Another possibility is heavy neutral leptons. These are cousins of the neutrino but much heavier, in the MeV to GeV mass range. They wouldn't oscillate like the light sterile neutrinos we were looking for. Instead, they would be produced in the beam and then decay inside the detector. If they decay into a photon or an electron-positron pair, they could mimic the signal we have been seeing. This is a sort of zombie sterile neutrino theory. The particle exists, but it is heavy and unstable rather than light and ghostly. Or perhaps it is axion-like particles, strange light bosons predicted by string theory that can decay into two photons. If those photons are merged together, they fool the old detectors. But maybe, just maybe, MicroBooNE can unzip them and reveal their true nature. This result, this null result, is often framed as a failure in the popular press. Headlines will say, "Experiment finds nothing." But in science, a null result is a triumph. It is a successful failure. For 20 years, the sterile neutrino hypothesis hung over the field like a thick fog. It consumed theoretical resources and experimental design. By proving it wrong, MicroBooNE has cleared that fog. It has forced us to stop looking for the easy answer and start looking in the darker, more complex corners of theoretical space. The search is far from over. In fact, Fermilab is doubling down. MicroBooNE is part of a trio of detectors called the Short Baseline Neutrino Program. It is joined by SBND, which sits very close to the beam source to characterize the neutrinos before they oscillate, and Icarus, a massive detector that sits far away. Together, they will act as a single, multi-stage system to track the evolution of the beam in real time. And beyond that, we are building DUNE, the Deep Underground Neutrino Experiment. This is the moonshot. We are blasting a beam of neutrinos, 1,300 kilometers through the Earth's crust from Illinois to a colossal underground detector in South Dakota. DUNE will use the same liquid argon technology pioneered by MicroBooNE, but on a scale massive enough to unlock the secrets of why matter exists at all. So while the sterile neutrino might be dead, the mystery is more alive than ever. The sterile void is not empty. It is just waiting for us to ask the right question. And that is the beauty of physics. We build these cathedrals of metal and argon. We cool them to cryogenic temperatures, and we stare into the darkness waiting for a flicker of light to tell us who we are and where we came from. The ghost we were hunting wasn't there, but the hunt itself has led us into even deeper woods, and the game is afoot. Thank you for listening to G Fun Facts Online. If you enjoyed this deep dive into the subatomic world, make sure to subscribe for more science that respects your intelligence.